So we've been running this meetup for the last 6 months. Those that are new to it, here's some of the sessions coming up until the end of the year. There's probably going to be one more based on cybersecurity, but so the next one up is on Apache NiFi and MiniFi. Basically, if you care about IoT, running, sensors, kind of tracking, that would be a good topic to talk. And what I try to do is bring some, engineering staff to talk about it. So, like today, we have Enis and Maryann Xue. They're basically writing the code that runs Phoenix in HBase. So that's what we basically try to do, get the data straight from the source. So September 13th, Bloomberg doesn't run on Bari, so I'm not even going to mention it. Then if you care about HBase in Phoenix, in October, we have another committer coming in. And if you care about REST servers and how we implemented the Phoenix query server, that will be a good discussion to hear. As well as I requested that he also does a HBase deep dive. So there will be 2 sessions done by one person. And then we have Apache Spark and Zeppelin data science workshop. We did one on Spark 101 a few months ago. That was pretty successful as far as audience. We had probably 3 times as many people. That's not much, but I can't blame for the weather, right? So yeah, that's basically it. And like I said, there will be in December a cybersecurity workshop. So we are hiring, but since this is mostly Bloomberg, I'm only going to say that thank you, Bloomberg, for hosting us. This was really a pain to find a venue. I want to thank Enis and Maryann, especially in this weather, to come and do the talks. I was expecting someone to cancel. Slides for today's presentation. We will, I'll coordinate it and I'll post it on the Meetup page. This talk is being recorded. So if you do have a question, please use the mics. That way we'll be able to capture every question and every answer. And if you'd like to present, please talk to me. My email address is over there. And if you like our meetup, if you don't like it, if you just have some general feedback, please post on the comment section. We do have a Stack Overflow kind of forum where you can ask general questions about our platform. Please leverage it. If Stack Overflow is not going to answer your questions, because we have guys like Enis watching the tracks and really answering those questions. So you get best of both worlds. You get the mailing list, yes, but they tend to be more noisy. So this is probably a good forum as well to try. And for the 2 people that are not from Bloomberg, Bloomberg is hiring as well. So there's a list of open positions. I think Bloomberg also, they do open source as well. There's about 12 JIRAs there. One I just saw committed the other day to our code branch. And there's a Chef Bach code that Clay's been working hard for a few years already. If these topics are of interest to you, definitely apply. All right, thank you guys. And Enis is coming up right now.
All right, thanks, Adam. I think I don't need the mic. Hold on. All right, so we're going to talk about Apache Phoenix past, present, and future of the SQL over HBase. A little bit about me. I'm a committed NPMC member at HBase, Phoenix, and Hadoop for some time, and I'm a Phoenix and HBase developer at Hortonworks. That's my Twitter. And big disclaimer: I'm not a SQL expert. Maryann who's giving the next talk. She's the best expert ever. So if you have like query planning, query optimization kind of questions, ask her. If you have HBase questions, storage, that kind of thing, you can ask me as well as her as well. So we're going to divide the talk into three. In the first part, we're going to talk about, let me come here, I can read from there. We're going to talk about the past, why we, not we, but why Phoenix came to be, what it has, and what's the current architecture. In the second part, we're going to talk about the present. We're going to talk about the recent features, what went into Phoenix in the recent releases lately. We're going to talk about query server and everything. And in the last part, we're going to talk about the future of Phoenix, some of the open ticket items, and some of the up-and-coming features. All right? All right, so this is the obligatory slide. Who uses Phoenix? Everybody uses Phoenix. As you can see, obviously, it got started in Salesforce. Now a lot of people are using it. In Hortonworks, we have been shipping Phoenix for the last 3-4 releases. It's getting a lot of traction, I would say. Most of the HBase customers either start with HBase and move into Phoenix nowadays, or just start with Phoenix. All right, so the basics. It's just the first slide is the first point is a joke. We hope that everybody is familiar with HBase because we won't cover it, hopefully. So what is wrong with pure HBase? So HBase is a great thing. I've been working with HBase for the last 4.5 years, but it's a low-level execution engine. Not execution, sorry, it's a low-level database engine. So HBase is great for storage, and if you know and okay with writing Java code to do what you want, HBase is a very powerful tool that you can do very optimized and very high throughput stuff. But what HBase lacks is a higher level language that you can use without writing a lot of code. So to get anything production ready in HBase, you have to write your Java code for whatever you want to do. In the end, once you have all the pieces ready, it will be awesome. It will be like using the motor, the engine by yourself. But it's again it's kind of like too low level in the sense of a database engine. So Phoenix is exactly coming on top of HBase and filling the gap in between the developer and the application and the underlying storage. So what Phoenix is giving HBase is a relational layer, as well as all the good stuff that's coming in SQL, like data types, query execution, planning, and everything. And Phoenix is helping the developers to get stuff done in HBase way easier than just using HBase as a pure HBase thing. Why not Hive, Spark SQL, or any other SQL or Hadoop solution rather than Phoenix? It's like everybody from time to time asks me the same question. It's very simple. If you look at Spark SQL, Hive, or any other MPP databases, they can do maybe 10 queries per second, 100 queries per second. Phoenix, we can do 100,000 queries per second. And if you want to do 1 millisecond queries, you cannot launch a yarn job. You cannot launch a huge execution framework to do whatever you want. You want to do point queries or very fast and super low latency queries, then you have to use something like Phoenix. All right, and most of the engines again, Spark SQL or Hive, they are for analytics queries, columnar data, and going over a huge volume of data. Phoenix is more like OLTP kind of workloads where you would care more about the latency rather than the throughput. All right, why SQL? Again, we've talked about this. Doing the same thing in SQL versus HBase row is very different. As you can see, this is a select statement with a simple where clause. You can do the same thing in HBase with this code. But obviously, you have to write this code. You have to test this. You have to make sure that this particular code is shipped with your application and everything. Or otherwise, you can just write this query in like a tool like Zeppelin, for example, or you can use SQLite, you can use Squirrel, you can use any JDBC compliant thing just to query the data from HBase, right? So Zeppelin is a great tool. Again, like you can use other JDBC or ODBC interfaces to query directly. All right, so quick summary on the HBase architecture. I'll cover this real quick. So the application sits on top and uses the HBase client, right? There's Zookeeper over there, and there are region servers which are sitting on top of the data nodes, and the data will be divided into different regions coming from different tables, and the client will talk to these region servers to do reads and writes, right? So this is the basic HBase architecture. Once Phoenix comes into play, not a lot of things change as part of the architecture, as you can see. The blue boxes here are Phoenix parts. So Phoenix injects an RPC endpoint, which is inside the region server process. And in Phoenix, it can also inject custom code into Phoenix-defined tables. So as you can see, some of the tables do not have the blue boxes, which means that in a cluster, both HBase and Phoenix tables can live at the same time. As well as you have one blue box sitting over there. It's called the JDBC Phoenix client. That is the Phoenix client, which embeds an HBase client underlying. Your application will be using the Phoenix JDBC client, which in turn will be using the HBase client. But that whole HBase layer would be transparent to your application. You would just be using the JDBC interfaces. All right. Again, we've talked about some of this, but Phoenix gives you SQL data types, schemas, DDL statements, composite primary keys. You can use, like we were talking with Adam earlier today, you can define, you can have an already existing HBase table and define and map a Phoenix table on top of the HBase table, and then be able to query from Phoenix. You can either write from HBase, read from Phoenix. You can do salting, parallel scans, skip scans, filter pushdowns, statistics. All of these features are coming for free from Phoenix by just using it. We're going to go into details of some of these shortly. So here's an example of a DDL. This is standard SQL. As you can see, it's create table if not accessed. It's a metric record table. You declare the columns that you want. You declare the primary key, which is a concatenation of the metric name, host name, and the server time. So this would be the primary key, which would be mapped into the HBase's row key. And you say you can even use HBase level features like the TTL, the data block encoding, and everything. And you can say here are my split points and everything. So going forward, this is how the data would be kept. As you can see, in terms of HBase, HBase is kind of like a giant sparse map, which is ordered in the sort order. So there is two different sort orders. There is one sort order from left to right, as well as top to bottom, right? So everything will be ordered by the natural sorting order. Since we have defined the Phoenix table which has these three primary keys. As you can see, the primary key constraint there. These first three columns, from a Phoenix perspective, will be concatenated together, which would form the HBase's row key. And all the other columns that Phoenix defines would be mapped as different HBase level columns. And your data would be still kept in the HBase's sort order. Okay? So we're going to talk about some of the query plans and some of the goodies that you would, again, get with Phoenix. So this is an example of a parallel scan that you would get by just doing the previous DDL statement and doing a select star from metric record. So, for example, in this case, as in most of the databases, if you do an explain and give the query, then you would get the query plan. The blue query plan here, I don't know whether it's readable or not, but it says client four-chunk parallel one-way full scan over the metrics table. So what happens is that once you do this query, the Phoenix client will know that the data is in 4 different regions. And then since the data is in 4 different regions and we don't care about the query sort order, then we will do a 4-way parallel scan. The Phoenix will drive the scan for you and then give the results back to the client. All right? A slightly more complex example would be a filter push down. So let's say that you're doing a select star again, but you want to do server time is greater than now -7. So you're asking for the last 7 days worth of data, for example. So in this case, if you do the explain plan, what you would see is that the same statements here versus it will say server filter by. And then since it says server filter, what it means is that this filter, this code for the filter will be executed on the server side. So this filter will be evaluated for every row from the server side, and only the rows passing this filter will be sent back to the client. So obviously, this would be much more optimal way to execute this query. Yet another slightly more complex example would be a skip scan. So let's say that this time you want to do the same query, but you would say metric name is like ABC, and host name is in host 1 or host 2. So in this case, what would Phoenix do is that it would execute the what's called a skip scan. A skip scan is more like it will start the scan, and then because we know that the host name is the second column in the primary key construct, then we can read some data, and as long as we know where to skip, we will skip the scan to the next data where the data lives. Then we will skip. We will read more. Then we will skip to the other location. We will read more. So this is an optimal way of executing this kind of queries. All right. Yet another example would be a top-down query. A top-down query is like, I want to get the same metrics for the last 7 days, but order the results by host name and give me the top 5. Okay. So this kind of query would be, again, like pushed into the server side. So what it will achieve is that each of these servers will drive the scan, and they would have the top 5 of every host name buffered up in the memory, and then the client, they will only return the top n to the client, and then the client will do the final merge sort. As you can see in the explain plan, the client will get the top 5 results from each server, and then it will be executing the query. All right? Again, another example would be the aggregation. This is similar to the top-end case, where we would do a group by and an order by. In this case as well, as you can see, in the query plan, we would do a server-side aggregate where the servers will each individually aggregate the query, and then the client will do a merge sort. So this kind of queries are perfect for Phoenix because they are all like distributing the work into different servers, and then the client would be doing the final merge. All right, so Phoenix definitely has some support for joins. We have 2 different join implementations. Again, Maryann can talk about this way better than me. So in terms of the grammar, inner joins, full auto joins, and cross joins are supported, and semi-joins and anti-joins are also supported. We can do a merge join or a hash join. I think we won't go into details of any of these, but you can think about the hash join as computing the hash plan, sending out the hash plan to each region server, and then each region server will do the hash join for you. There's like predicate pushdowns and other optimizations for the joins as well. I can discuss offline if you guys are interested in how the joins are executed. Phoenix can execute most of the TBCH queries, which is a pretty good feature. There's no nested loop join yet, but with the calci support, more improvements and better SQL support is coming. So Maryann's talk will also cover these. And there is also no statistical guide into selecting the joins. So like if you know, for example, you want a hash join or a sort merge join, you can hint it. But there's no like looking at the statistics of I can do this join much more efficiently as of yet. Phoenix, again, Phoenix is not a replacement for Hive, Spark SQL, or other MPP databases. Phoenix itself does not have the execution layer like a MapReduce or Tez or Spark. So it's not a generic execution engine. What it means is that there's no server-to-server exchange that's happening when the queries are planned. So what I tell in other contexts is that you can think about most of the Phoenix's execution as multi-map, single reduce, if you are familiar with the MapReduce model. So what happens in Phoenix is that the map side of the plan will be executed from the region servers in a parallel manner, and then the client will do the final merge, which is kind of like the reduce plan. All right. Phoenix also has secondary indexing, which is a very popular feature in HBase as well as Phoenix. So again, as we've talked, HBase, all the data is kept in sorted order, and there's only one sort order in HBase. So a single table in HBase can only be sorted by the row key sort order, and we will sort the primary key first, then the columns. But there's only one global sort order. But secondary indexing, by definition, means that you want a different sort order than your primary sort order, right? So that's the definition of the secondary index. When you define a global Phoenix secondary index, what happens is that there will be one HBase table for your data, and there will be another HBase table for your secondary index data, right? If you have more than one secondary index, there will be one table, one HBase table corresponding to your each of your secondary indices, right? So as you want a different sort order for your secondary index data, obviously the secondary index would be sorting the data based on your secondary index condition. So if you have primary key for your column A, B, C, and your secondary index for column D, obviously the secondary index HBase table will have the primary key for column D, right? It will be a different sort order. We have 2 different secondary index implementations. One is called the global index. The other one is called the local index. The global one is most likely the one you would use. The global one is obviously keeping a global order for everything. The local one is an interesting one. Instead of having a global sort order, the local one will have a local sort order per region. So in an HBase table, you can have thousands of regions, and each of these regions will have, if you define the local index, each of these regions will have the data sorted in the primary sort order as well as the secondary sort order. So this helps in some particular workloads because in some cases you're okay with asking every region the same query and collecting the results for using the local index. But obviously, like if you're doing a point query and you want to access a single row, then using local indexes won't be good for you because it will be, you ask every region available to return the data for you, right? So in terms of the querying, indexes are covered. So what it means is that it's a SQL concept. So covered indexes means that in the index definition, you can say, I want these columns to get saved together with the index data. So what it in the end does is that the secondary index will keep those columns that's not part of the index, but still you want these columns to be covered. So when you're asking a query to the secondary index, if it's a covered column, it will directly come from the same scan that's happening. So why is this important? Is that think about a query that will return 1 million results, right? So since unlike a single node database, HBase is a distributed database which is run on hundreds of nodes or thousands of nodes. If you have a query which would return 1 million results, we cannot do 1 million point lookups for a given single scan, right? This will be horrible in terms of performance. It will take like many, many minutes. That's why having covered columns makes a lot of sense because the covered columns is a way to denormalize the data and keep the data together in the index so that you won't have to go back to the primary again and again and again and do random lookups into the primary data, right? This slide just gives you pros and cons versus global versus local index. We've talked about most of this stuff already. So the global index is the one you would likely use. Local index would be good for some specific use cases where you know that the query is okay to hit every region. Every query hitting every region is okay because, for example, if you're doing an aggregate, for example, then using this kind of local indexes would be good for you. All right, so the second part would be what is new what is new and recent in Phoenix. So I don't think we will have the time to go into all of these features, but feel free to catch me offline if you have questions. So 4.4, Phoenix recent release is 4.8, which is today the release candidates are going on. 4.4 is I think a year-old release. It had a lot of features like functional indices, UDFs. The query server was new there. Union node support was there. MapReduce index builds. Spark integration was new in 4.4, and a lot of date functions. 4.5 came after client-side per statement metrics, select without from, altered table with views, and array functions were there. 4.6, row timestamp, which we will cover shortly, is new. Correlated variables, the trace UI is there. 4.7 is one of the major ones. The transaction support is there, secondary index, and perf performance was there, and stats as well. So row timestamps is a relatively new feature, which was one of the lacking things from Phoenix to HBase mapping. So HBase has this powerful feature for timestamps and keeping multiple versions of the data. So using this feature, you can make use of the native HBase timestamps from the Phoenix layer. So what it does is that you can define a pseudo column called the row timestamp. You can create a column which is a date column, for example, and then you can map this column to row timestamp as in this syntax. What it does is that every row will contain this pseudo row timestamp column. You can read this to access the native HBase timestamps, or you can set this from HBase native timestamps. So this allows, for example, if you have a time series use case and you want to access, for example, HBase's timestamps underlying Phoenix, this is a very powerful feature to make use of that. And for example, like if you have like a IoT use case or like metrics use case, for example, and you are having mostly time series queries, then you can use this row timestamp to filter the data from HBase layer so that the queries would be executing much faster than otherwise, right? Transactions is also fairly new in Phoenix. It uses a project called Tephra. So Tephra is giving pure snapshot isolation in HBase. It is completely optional now, this transactions. And this is released in 4.7 and would be probably GA in 5.0. And it does optimistic concurrency control for snapshot isolation. I don't think we will have the time to go over the Tephra architecture, but very quickly, Tephra will have two daemons running in a HA mode, which would be the transaction managers, and the clients sitting inside the Phoenix client would talk with the transaction manager to coordinate the read and write transactions for you. All right, this is the transaction lifecycle. We won't go into details. If you guys have any questions about any of these, feel free to catch me offline. Query server is also very new in Phoenix, but this has seen a lot of improvements, and in 4.8 and HTTP 2.5, this would be, I think, one of the major features. So the query server is similar to, in concept, the Hive query server 2, or for example, the HBase REST server. So it's kind of like a gateway, which is getting the query and then executing the query on your behalf. What will be the significance is that this Phoenix query server has a Thrift API to the outside, so that you won't be bounded by the Java and the regular Phoenix clients. So it already has a thin JDBC client with it, but there's also an ODBC client which can talk to this Phoenix query server from a C or C++ application using the ODBC spec, right? So in terms of the architecture, this is the not old, but this is the what's called the tick Phoenix client. Again, this is the same previous example. There are region servers running. Your application just uses the Phoenix client JDBC, which talks to the HBase client and then does the execution for you. So one thing about why this is called the tick client is that this Phoenix client has to also do some computation. For example, if you are doing an aggregate query, again, like as we've seen in the previous query plans, if you're doing a sort merge join, for example, each of these region servers will compute and sort the result for you, but the client will do the final merge sort join. So in this case, the application which embeds the Phoenix client has to do all of the work to do the sort and everything. But in most of the cases, you don't want the application layer, which is Tomcat or some other web server layer, to do the heavy lifting for you. So the Phoenix query server is perfect for these kind of cases, where in terms of architecturally, it just sits in between the region servers and your application. And these green boxes are the query server, right? So, there's a thin client which talks with these query servers, and each of these query servers have internally embeds the thick client. So the previous thick client that the application was using, so this is the previous slide. So this is the previous slide. This is the query server slide. So the previous thick client now is embedded inside the Phoenix query server. So you talk over Thrift to one of these guys, and one of these guys will execute the query for you, right? So this gives you definitely ODBC support, as well as having a thin layer which doesn't do any computation. All right, there is also other good stuff in 4.8 plus. There's shaded clients, so none of the dependencies from Maven would be exposed from Phoenix. There is Phoenix schema mapping directly to HBase namespaces mapping. That's also new in 4.8. Limit offset is also new in 4.8. We already had limit, but offset is new. All right, and the feature. There's a couple of things I want to talk about in this part. The first part is the local index. I think we've talked a little bit about it already. So 4.8 comes with local index feature being rebuilt. So we have done an extensive amount of work to rebuild the local indexing kind of from scratch. So previously, every local index was also another HBase table, which we were coordinating through the HBase's load balancer to make it so that the data table and the index regions are co-located. But in the 4.8 code bases, what happens is that the local index data is kept inside every region. So there is, for every local index, there won't be another HBase table. The local index data would be embedded within the region, and then the region will compute the local index data, the writes, and everything, as well as this makes it so that the local index data is committed as an atomic operation together with the primary data, so that the visibility and the consistency guarantees are taken care of for the local indexing. This also gives a lot of performance benefits in terms of the writes coming in, as well as we're circumventing all of the co-location issues and everything previously with the local indexing feature. So long story short, local indexes, you can use it in 4.8 plus. Please don't use it before then. Cal-side integration, Maryann has this whole talk about it. So we're going to skip that. Hive integration is also pretty new. So Phoenix already had Spark integration. So Hive integration is similar to the way that Phoenix Spark integration works. Again, as I've talked, why do you need Hive integration or Spark integration from Phoenix in the first place? Is that Phoenix cannot execute a huge table join versus another huge table join. It's not the right tool for this. If you have, but if you still want to execute those kind of queries, or for example, if some of the data lives in Phoenix, but you want to join this with another data in Hive, for example, or if you have like a Lambda use case where the most recent data lives in Phoenix and the other data lives in HDFS in Spark, then you can use either the Phoenix Spark integration or the Phoenix Hive integration to basically keep the data in Phoenix, read and write through Phoenix, as well as query from Hive or Spark so that you would get all the benefits of the yarn scheduling and shuffle improvements and distributed execution. Anyway, so again, Hive is a very rich and generic execution engine already. And this integration gives Hive the ability to read and write Phoenix tables directly. So in this case, you would still have the Phoenix table. You would declare the same Phoenix table as a Hive table as well, as an external Hive table. And then you would query directly from HiveQL. Hive will compute the query plan and execute it through Tez. But for example, the predicate pushdowns, salting, partitioning, data locality, secondary indices, and everything will be automatically taken care of, because what happens is that Hive will give parts of the query into Phoenix. Phoenix will also compute with the query plan. The Phoenix will return the underlying scan objects into Hive, which then Hive uses to execute the query. So for example, if you're using, again, any of these features like salting or secondary indexing, it will automatically work in the sense that the plan will be as optimal as possible. This is just a quick slide for what are some like missing topics that the Phoenix community is tracking. JSON support is one, TPCH, MicroStrategy, and Tableau. Again, certification of all of these is definitely a big effort going on. Scope integration, OMIT-based transactions, some dogfooding. I don't want to go into details there. Basically, biometric server and Yarn using it. The struct type, cost-based optimization, and security, like SQL level access control and role-based models. These are like tracked inside the community with varying degrees of being done. All right, there's definitely some great info on the web page, as well as like the Phoenix community is pretty friendly. If you have any questions, feel free to ask it in the mailing list, or again, like catch us offline. The roadmap is over there as well as like the extensive documentation about all the existing features is there in the website. All right, thanks. So I think we're gonna do the second talk, then do the queries, Q&A. Right.
So thank Enis for giving such a good introductory talk. So So I'm going to go into more details about the new query optimization framework in Phoenix. So I'm Maryann. I work for Intel, and I'm a PMC member of Apache Phoenix, and also a committer of Apache Calcite project. So, like Enis said, like he has, like I guess like maybe some of you here are pretty familiar with Phoenix already, and even if you're not, I mean you've already got a pretty good idea of what Phoenix is from Enis's talk. So I'm gonna go through this really quickly. So Phoenix, first of all, is a query engine which transforms SQL queries, as into native H-based calls, and it's trying to push as much work as possible into the into the H-based cluster for parallel execution, and also has a metadata repository. The DDL, like it allows you to use DDL statements to create, Phoenix tables, which is essentially H-based tables, but which are strongly typed. And also it has, from 4.8, it has transaction support, and which is a great, add-on feature. And and also we now have table statistics, which are basically something we call guideposts. And these guideposts are just, they're collected, in the background during H-based compaction, and are actually used by the client to decide the most efficient way to drive parallel execution. And last thing is it's a JDBC driver, so you can just use it as any other JDBC driver. So let's look into some advanced features we either already have or that are listed on our roadmap. So first of all is we have global and local secondary indexes. And there is also another type of secondary index, which is kind of orthogonal, which is the immutable index. So it assumes that your data doesn't, you only add new data to your tables, not, without making any changes to the existing rows or deleting them. And so we've been working pretty hard, since Phoenix started, to achieve strong SQL language compliance. And we also looking to add windowed aggregates into our feature list. And it's also it'd be very nice to have easy connectivity or integration with other database or big data components out there. So, and the integration, it's not about, simply pushing a H-based scan down into Phoenix. It could be more interactive or more fine-grained integration. And so these features or nice things we're looking to have actually will create some architectural pain that, we've decided at this point that we need something new to do these things right. So first of all, what kind of problem we can see in this, in those, features we already have. The first example is about the secondary index problem. So in this example, we're going to have a very simple employee table, which only has two fields, the employee ID and the name field. And so, like Enis said, so the H-based table or whatever Phoenix table is only ordered one dimension, like the primary key. So here we have the primary key called employee ID. So the data table, employee table, is going to be sorted on this employee ID column. And so we're going to have another index table, which is indexed on the name field. So this index table is going to be ordered on the on the name column. So the first query we have here is select from employee table order by name. And apparently, so we should use this index table, the index table which is ordered on the name field, so that we can, when we're doing this query, you can avoid any type of sorting. And so Phoenix now already has this like strategy, like using static matching, certain like patterns in the queries to figure out like which table we should use. For example, in the first example, Phoenix is going to recognize this order by clause, and definitely it's going to use the index table as we expect. And so the second query is going to select from the employee table where employee ID is greater than 100. And again, this where clause is like gives a pretty obvious hint that we should use the data table instead, so that we can have a range scan instead of a full scan on the when we scan the employee table. And Phoenix is also able to recognize this where clause pattern, and it's also going to use the employee table without any hint. And so how about this third query, which has both clauses in the same query? So it's going to select from the employee table where employee ID is greater than 100, order by name. So it's not so obvious that we can easily see like which table is going to give us a lower cost, right? And also, so here, we can see that this is when we need a cost-based, optimization. And the statistics I just talked about, the table of statistics, can be very helpful here. So it's say if we have like the number of bytes of each of these tables and the number of row counts each of these tables, and we can cost probably the order by operation together with the scan operation, like respectively, using these two different tables, and we're going to figure out like which plan is going to generate a overall lower cost. So this is the kind of a solution. Like we decided to use Phoenix together with Apache Calcite, and both projects are Apache top-level Apache projects. And this work is going to involve like changes to both projects. And so like basically the majority of the work in Phoenix is being done on a Phoenix feature branch. Well, if we need anything like bug fixes or new interface or some changes in Calcite project, we're most likely to commit into the Calcite master branch. So the ultimate goals here are we're going to remove some redundant code, mostly in the Phoenix project, because we're going to use the Calcite front end, like the SQL parser, validator, query planner, everything. And so Phoenix, like the old code that does the same kind of job, is going to be eventually removed. And most important thing is we're going to have like improved planning, query planning, and which does this like the planning faster, and which generates the queries that run faster on the server side. And also we're going to get much better SQL compliance, the language compliance, just for free from the Calcite front end. And we'll have some nice SQL features as well, like probably like window aggregates and some SQL grammar support, and even the filter clause is kind of like a very new feature in the SQL standard. And of course, we'll have to achieve like close to full compatibility with the current Phoenix SQL and the API. So we started this work like the end of 2014, and right now we're pretty close to get the whole like existing Phoenix test suite run with the new calcite Phoenix, and we're looking to put in the formal release by the end of this year. So let's take a look at the current like Phoenix architecture. It's like pretty straightforward, like from top to bottom. It's just all the way from parser, and then gets translated into the Phoenix parsnode tree, and then to Phoenix expression tree. And then, then the compiler will convert the expression tree into a query plan. And this query plan is going to be executed on the Phoenix runtime to access the HBase data. And this is the original calcite architecture. And the calcite is kind of different from most of the other like database engines out there, because calcite, is not something that like goes from parser all the way to data access. Instead, it's just basically a query optimizer, a query planner, and so everything like the schema, like the data schema, the data engine, they're all kind of pluggable. And you can implement your own SQL operators, and rules, and optimization rules, and you can plug in your own statistics and your own cost model. And this is what Phoenix, when we put Phoenix and calcite together. So we actually plug in Phoenix data schema. Like we're also implementing Phoenix physical operators and Phoenix optimization rules, and we'll have our specific statistics fed into the planner and our own cost model. And but there will be a translation process, like from the calcite algebra into the original Phoenix query plan, and at the end it's going to execute it the same way as we do now onto the in the Phoenix runtime engine. And meanwhile, it's worth mentioning here that like we can also inherit this nice capability just from calcite of being able to connect to other database data sources, like other JDBC drivers or even other big data components that which whose adapter has already been implemented in calcite. And so just when we talk about cost-based optimization, so what does it exactly mean in the Phoenix context? So we know that we already have like a bunch of like very nice optimization, runtime optimizations in Phoenix, and also like we have like other like nice features, runtime features in Phoenix. Like we have filter pushdown, and then we can do range scan and skip scan instead of full scan. We also we do some optimization on sorting. We try to avoid sorting as much as possible. We sometimes try to push sort and limits through like union queries. We make use of like forward or reverse scan, whatever, and we have implemented like different aggregate strategies. We have different join implementations. And we also have this secondary index table that we can choose from, to make queries run faster. So the idea is Phoenix now does have some compiler strategy to figure out which of these schemes to use or which of these optimizations are going to benefit the query execution. But it's more like it's just a static matching strategy and static transformation. And a cost-based optimizer is going to make it possible for you to choose from choose from all possible combinations of filing all these potential optimization rules. It's kind of not trying to trim or limit the search space for best query plans. Instead, it's just keep all the plan candidates in the same place so that at the end of the day you can just choose one that has the best cost from all these potential query plans. The optimizer will do, yeah. Yes, the optimizer, yeah. And it's totally based on the cost of the query. So it wasn't before. So in Phoenix, Phoenix does have some kind of algorithm to figure out which, for example, which join algorithm it's going to use for join query, which aggregate strategy is going to use, or if at this place we can avoid sorting or not, whatever. But they are not just all combined. I'll have 2 extra examples that kind of illustrate this idea more clearly. And also I'd like to mention that these the points listed here, they're kind of all turn into when we adapt Phoenix with Calcite, we are turning these features or optimizations into operators and optimization rules in Calcite. This is a Calcite algebra. It's if you look at a diagram from bottom up, it's pretty straightforward. The query is select products dot name, count star from sales table, join products table using product ID, where sales dot discount is not now, group by products dot name, and order by count star descending. And first of all, we're going to have two the scans of the 2 tables. On top of them, we're going to have a join node. And then we'll apply a filter on top of the join, and then we'll do an aggregate based on the filter result. And then in the end, we'll have a sort operator. And so this is the second example today. It's using the same query as the last slide, and also the diagram, the original diagram. The algebra is the same as the last slide too, and so this is an illustration of how an existing optimization rule called filter into join rule works. This rule simply looks for a pattern like a filter node on top of a join node, and once it finds this pattern, it checks if the filter is only going to deal with one of the join input only. It's either side of the join. If it's dealing with both sides of the join, it's not going to work. And if this satisfies, it's going to push the filter through the join and down to the top of its input node. So on the right-hand side, you can see it's the It's the form of the algebra like after transformation. But it's also worth mentioning that, like both of these algebras are going to exist in the query planner for the length of query planning. So we're not eliminating the left-hand side from our choice. We're just keeping it until until in the end we can figure out like which one is cheaper.
You just keep saying we are keeping. Who are we? I mean, is it optimizer?
The optimizer, I'm sorry.
So why would optimizer keep the left side if right side is clearly more performant?
I mean, basically, actually, you have two different strategies in query planning. One is, yeah. Also, his question is like why we still want to keep the left-hand side while it's apparently like more expensive than the right-hand side. So the answer is like basically we have kind of like two planning strategies like in a query planner. One is the kind of the static strategy is like we can figure out like most of the rules if they work. I mean after they work, the transformation result is going to be cheaper. Like in this example, most likely it's going to be cheaper. Right. Yeah, the right one, right? And the other strategy is called like totally cost-based. I mean, it doesn't know like at this point, because other transformation can happen on the left-hand side as well. I mean, in this example, it's not a good example of, what kind of transformation can make the left-hand side cheaper, but it is possible. The left-hand side, we're keeping it because I mean, it's possible that some other transformation or some other optimization rule is going to match the left-hand side at some point, which will make it cheaper than its original form.
But who's determining that? Calcite or your own logic?
I mean, calcite is not determining anything. Like it's only matching the rule and firing the rule and keep everything in the same pool of choice. And what other components that that connects with calcite does is just defining those rules, like defining the whatever, if there is a rule called filter into join rule, defining such kind of rules. And these rules will just get filed by the planning framework. And in the end, what calcite does is just cost each tree like this, each algebra. And also like the connectors are going to define like how these algebra, like how each node is going to be cost. Like for a join node, like if you look at the number of rows of the join node, like you're going to apply a multiplier, whatever, you're going to have a cost. That's up to each connector's implementation. Like for example, Phoenix is going to decide the cost of a join node depending, depending on the number of rows it gets into the join node, whatever. So what the framework does is just it keeps firing these rows as long as there's a match, and keep all possible algebra there as they are, and it's going to cost like each form of implementable algebra, and then it can compare like which gives the cheapest cost, because it doesn't really know. It doesn't. I mean, from this diagram, it doesn't. I mean, the planner doesn't really know like which is going to be cheaper. I mean, unless it just computes the cost, right? Until it computes the cost, it doesn't know. Yeah. So we have like two join strategies. One is the hash join, the other is sort merge join, and hash join is definitely like good for like either side. Either input is very small that can fit into memory, and this is also called broadcast join. And sort merge join is good when, like hash join can do its job well. Like both inputs are pretty big, so neither of them can fit into memory. But hash join apparently, I mean, it can cause like out of memory error. And sort merge join is usually, I mean, like it's usually more expensive because both sides of the input have to be sorted on the join key before it can perform the join. So we figure if we can better exploit the sortedness of the join input and exploit the sortedness of the join output, we might probably get more efficient, like, join execution. So this is the original, like, calcite algebra. This is the logical algebra. Like, there is a join node on top of two table scans. Okay, I'll explain the query quickly. So it's going to select employee ID, employee name, department name, location. From employee table, join department table using department number, order by the department number of the department table. And so the algebra is very simple, like a join node on top of two scans, and there's a sort on top of the join, and then a project. Like there can be a whole bunch of like plan candidates, like in the in the planner, but we just list two of them from the candidates. They are the most promising candidates. On the left-hand side, it's going to use a hash join, like and it produces. This is the kind of physical algebra, but it's going to be like very similar to the logical algebra. And on the right-hand side, it's going to use a different strategy, which is the merge join. And so originally there have been 3 sort nodes in this diagram, but there's also a sort remove rule which got rid of the 2 of the sort node in this diagram. So originally it had been more expensive because if you think of this diagram as having 2 extra sort nodes, and it's going to perform like compared to the left-hand side, it's going to perform like 2 extra steps of sorting, and it's going to perform like a join operation and 2 scan operation as well. So it's just like it's more expensive because it could have like 2 more extra steps of sorting. But after the sort remove rule works, you can see that there's only 1 sort node left here sitting on top of the scan of the employee table. And when you compare the 2 diagrams after the sort remove rule, it's apparent that the right-hand side is actually going to be cheaper because the sort node, the sorting is going to be applied on the scan result of the employee table, while candidate 1 is going to sort the joint result of the 2 tables. So actually, when I ran a simple test on a single node cluster, it actually gave me like 30% saved time. So I hope I've made this point clear. Like before sort remove rule kicked in, we actually got a plan that we got a plan. The candidate 2 is more expensive than candidate 1. But we are not kicking this out of the planner, because otherwise we could have missed this opportunity of applying sort remove rule. And so after applying the sort remove rule, we're actually getting a plan, which again is even cheaper than candidate 1. So this is like the original. I mean, this is the Phoenix query plan translated from candidate 1 and candidate 2, and um, and it's interesting that candidate 1 happened to be what exactly Phoenix, the old Phoenix compiler is going to generate, because Phoenix compiler most likely is going to think that hash join is going to be cheaper because it doesn't involve too much sorting. But in this example, after we exploited the sortness of the join input and the join output, we're actually getting a plan using merge join that runs faster. So we can come back to look at the first example we had today about the secondary index. So we are modeling Phoenix secondary index as calcite's materialized view. And here, a calcite materialized view is actually matching like some part of the algebra, and it's going to transform the matched node into the secondary index table we've already defined. So I'm not going to go into more details, but the simple idea is on the left-hand side is the original using the original data table. So it's going to scan the employee table, filter on the employee ID, and then just sort by the name field. And it also happens that the bottom two nodes can be combined into a range scan, and so it's not going to. I mean, it's going to produce. Anyway, I'll talk about cost later. And on the right-hand side, it recognizes the pattern of this like sorts on top of employee table, and it's going to replace this pattern with the index table. And so the right-hand side plan is going to be scan the index table and filter by the employee ID, and then perform the right project. Otherwise, because it will be like name first instead of employee ID, whatever. So this way we can clearly like see the cost of each node. Like on the left-hand side, the range scan is going to produce, for example, we have 100, probably we have 1,000 employees. And so after applying this filter and after we do a range scan, we're going to scan probably just 900 rows instead of doing scanning 1,000 rows and doing a filter on top of this 1,000 node. We're just skipping the first 100 rows at all. But then we're going to do a sort. If we like cost it, for example, like n log n, it's going to be like 6,000 something, the cost. But this is an example. I mean, we don't actually do this exactly, but it's just illustrating how the cost is computed. And on the left-hand and around right-hand side is going to scan the employee. It's going to scan the index table, which is 1,000 rows again, and applying the filter, which is not a like 1,000 rows operation on top of the scanned result. And then after the filter, we're going to get 900 rows, and we're going to do the project on top of the 900 rows. And so if we sum up these numbers together, we can see that for this specific query, the index table is going to be produce a lower cost. So aside from this nice like improvement we get in cost-based query planning, we also get some other very significant features by integrating with Apache Calcite. First of all, we'll get the missing SQL support like a lot of SQL grammars we're struggling to have. And also we can like further explore the usage of materialized views, not only for secondary indexes we already have, maybe for other like user maintained like summary tables, whatever. And also one of the most important things is we can now have we can now easily connect to other calcite adapters, including all kinds of JDBC sources. And so we are happy to announce that we already have like in Phoenix and Drill integration working. And this thing we call it Drillix. And this is an example of like the different level of integration we can have with Drillix. It's not only about like for example in this query we're doing a group by aggregation on the employee table. So we are not simply pushing just the Phoenix table scan into the Phoenix runtime. Instead, we are also delegating like part of the aggregation operation into the Phoenix runtime too. So the two green nodes here are actually the Phoenix part of work. And then the partial aggregate, like the server side, like aggregate results are going to be fed into the drill runtime. And it's going to be, the data is going to be converted into the drill format, and then drill will do the final aggregate. The idea here of doing like partial aggregate inside Phoenix runtime is like we can return like less rows into the client here, which is drill here. I return to the client less, a smaller size of the data by doing the aggregate beforehand. And so it's going to be more efficient. All right, thank you for coming to my talk. If you have any questions, we're here to, yeah.
With drill, where drill comes and why do you need even the first local processing by Phoenix if drill does it as well? If you delegate the upper level to drill, is there something wrong with this drill portions that you substitute with green stuff?
Yeah.
Because drill, as far as I know, also does the same thing on HBase and MapRDB.
Exactly. Drill, first of all, like drill models a aggregation as a like multi-step, like distributed operation. Like first of all, it has a local, whatever, partial aggregation on each server. And then, it does a final aggregation based on these partial results. The idea is here is we are trying to let the HBase server return less rows or like smaller size data set back to drill. Yeah.
Well, yes, that's clear, but you're doing this probably by applying filters, right? Because if you don't apply filters and you don't query it just by the key, then it goes to full table scan in HBase. So if you're propagating this stuff to the HBase, then as far as I know, drill does the same thing. So I'm not sure what is the value of these two green entities.
No, here this is an aggregate. So if you're doing an aggregate, it's most likely it's going to reduce the number of rows than the original table.
That's right. I don't disagree with it. But what I'm saying, that drill does it as well. So why do you need to replace a portion of drill with this green stuff?
Yeah, that is, yeah.
But as far as I understand, the original data is stored inside the HBase.
I guess I haven't made this point very clearly. I'll just say it again. So here, like there, I mean, that we have a network cost anyway, if coming from HBase to the drill servers. So we are trying to reduce this network cost. So by doing this aggregate inside Phoenix, actually inside HBase, like Phoenix is doing this on coprocessors. So it's doing this inside HBase servers. So it's returning less rows, and Phoenix use a more compact data structure other than each key value for each column.
Okay, so you basically added the extra layer of filtering in addition to HBase filtering. You added your own filtering and implemented it through the processors of the HBase.
I don't think this example is about filters. This example is about aggregates. So aggregates, like for most aggregates, you're expecting if we have 1,000 rows, for example, in a table, if you're doing an aggregate, it's going to return a distinct value of your 1,000 rows, right? Yeah, that's the idea. Yeah. Yeah, exactly.
Other question?
I have a question on if you have any slides or a documentation that you can point us to regarding performance for joins and for second indexes. Maybe if we can compare them to something that we know, like maybe DB2, IBM DB2, or maybe like Oracle or so. It's just like the performance, like if we can compare apple to apple, say how far we are from the joins. Benchmark test. Like, yeah, benchmarks, basically.
That? Or
I don't know of any. Yeah.
All right.
I mean, I don't know of any like latest performance benchmark we've done.
Yeah, so there is no like official numbers for TPC-H comparisons between Oracle RAC versus Phoenix or anything like that. In terms of like raw performance coming from HBase, we know that HBase is capable of delivering whatever the other databases deliver in terms of both latency and throughput and more. For like secondary indexing and other like types of other features, like for example, secondary indexing is implemented in such a way that it's one write and one other write for every secondary index value, right? So like in terms of the performance, on the right side, it would be like you would pay the price of doing one write per secondary index. So like, and on the querying side, for example, you would be, again, it depends on what covered columns there are and whether you're accessing the covered columns and whether you're doing a join between the secondary index and the primary data, but it would depend on the query plan of how it executes and everything. But in the end, it goes and executes as a regular HBase scan or a scan plus a point lookup into HBase. So long story short, it depends. But there is again some work going on for running TPC-H queries, not for measuring performance versus this database, that database, but just for correctness purposes. And I think going forward, we will probably have some performance numbers at least. But these kind of official numbers and everything I don't think Phoenix would be in that game anytime soon.
Okay. Another question is regarding replication and so you want to be up all the time. So if one cluster fails, we point to another cluster, but then how do we make these two clusters in sync regarding the Phoenix tables? Is there any work on that or not?
I think it's a great question. So HBase has intercluster replication, which is working at the HBase level. It's not synchronous replication. It is asynchronous replication where every region server pushes the updates to the other cluster asynchronously. Normally, the latencies are usually pretty small in the like hundreds of milliseconds perspective. There's even like work coming up for reducing those latencies even further. From Phoenix perspective, so this is just HBase's own intercluster replication. From Phoenix's perspective, there is a couple of nuances for replicating the data. Like for example, Phoenix has its own schema and catalog information and everything, which is kept in some other table. So you have to be careful of what to replicate there, what not to replicate there, kind of thing. As well as like, for example, if you are replicating a table with multiple secondary indices, for example, the consistency between the secondary index data versus the actual data table, you want to keep it the same in your primary cluster versus backup cluster kind of thing. So we would be taking on the work to make Phoenix replication to be a kind of thin layer on top of the HBase's replication, so that, like for example, catalog data would be replicated as well as like secondary index will be rebuilt on the other side and everything. So that work is coming up. I don't know when it will come up. I think probably 5.0 timeframe. Another question?
You already talked about a little bit about the global index writing. Can you expand that a little bit maybe and talk about like the impact of global indexes on really high volume write type of payloads or workloads?
Mm-hmm. Yeah, it's a great question. So so HBase does not do HBase or Phoenix does not do anything magical, right? So since like we have to resort the data in some other format for every secondary index that's defined, a single write coming in would be turned into another write per secondary index. I've seen a customer talking about 60 indexes for a single column. Sorry, single table, which I don't know whether it worked or not. But the thing is that like if you have one data table, 5 indices, like every write coming in would be 6 writes. But we would be batching those writes as well as we would be like doing these writes in a kind of asynchronous manner. You won't be affected in terms of the latencies that much. But because of the covered indexes as well, like the data that you're writing is multiplied as well. So covered indexes, again, I tried to cover that, but think about it as replicating the columns of the primary column in every other like index that contains these covered columns. This helps in the query because you don't have to go back and forth between the data table and the index table, but you're paying the price at the right side, right? So if you know that you would be write heavy but not read heavy, then you can have not covered columns but just the second index columns, for example. But every query has to go to the secondary index, then go back to the primary thing. One other thing that's important would be that a write coming in for secondary indexing usually does a get on the same data, on the same, the region, because it's kind of like, for example, if the table contains 10 columns, a write comes in to change one column, which is also in the secondary index, then I have to read all the other columns so that I would update the secondary index kind of thing. So sometimes the writes coming in will turn into reads as well. That's also a thing to consider if you have super high throughput writes. There is, she mentioned already, there is a thing called an immutable table, which means that if I write a row, I cannot modify it. Phoenix assumes that you would only write new rows. This is pretty useful for like IoT, again, kind of scenarios where the data doesn't change, you would only add more data. If you have such data model, then using immutable tables would be perfect because you don't have to do any of these like gets and everything. The client would be computing all the writes for secondary indices and then pushing them down to the regular batch writes manner kind of thing.
So are there any so what are the latencies between the writes to the secondary index tables? Are we talking about what, microseconds, single milliseconds, double digit milliseconds?
Yeah, so it's also a very good question. So so the way that the Phoenix's mutable secondary indexes work today is that the write will come into the primary tables region, and then that particular server will be pushing the secondary index writes in line with the processing of the actual write to the data table. So in terms of latencies, it will be milliseconds, a couple of milliseconds. And this, the way it works is that this data table's update won't be visible unless all the index updates are pushed through, so that the visibility guarantee is a little bit better than eventual consistency, but still like the index mutations would be visible before the actual data mutation. But good thing is that in terms of correctness, it would always be correct, and even if there's failure conditions, we won't lose the secondary index data. Sure. Adam has a question, I think.
So correct me if I'm
Gray
wrong.
has a question.
Since you mentioned immutable tables, and Mohammed, who was in the crowd, he just left, talked about replication on the index table. With immutable tables, you can replicate, it's a simpler story, right? To replicate a table with many indexes.
Yes. So like today, replication already works between but you have to set it up in such a way that you would replicate all the tables that has the index data as well as the data and everything. And you have to define the same table in both of these places in terms of the schema and everything. But it works, but you kind of have to know what you are doing, kind of thing.
Two questions for you, actually. Just back to the drill question. I think there's Phoenix 2281, which is drill support for Phoenix, but it doesn't look like it has much updates. And I think this is the second time I've heard a presentation on drill on top of Phoenix. And I was wondering if there's maybe a better place to look for development on that. And completely unrelated second question is just, Enis, I think your slides had a mention of OMID transactions, but if I understand right, Phoenix was looking to use Tephra transactions, if I recall right. So I'm confused about both transaction layers being in Phoenix. So if you guys could just give some illumination on that.
Answer the first.
Yeah, this is a interesting question about drill and Phoenix. Actually, we started this work pretty early, and it didn't take us much effort to achieve to this level, because I forgot to mention that because both engines, once they they both use calcite as their like algebra representation and the same planning framework. It's just kind of like easy and straightforward, although we did have to do some work to adapt to the drill framework. But so right now, like the query side, it's like you can see that, you know, like we can do pretty sophisticated integration between the two components. But the only problem standing there is the usage of secondary index in drill and the Phoenix. So it's kind of like we still have to plug in that missing part for drill to recognize this alternative plan of using secondary indexes. Yeah.
Is the code anywhere by chance publicly available, or is it still just internal?
It's still on branches. Yeah, but also like what's like actually stopping us from getting there is drill. It's kind of like a historical thing. Like drill, like once were like kind of like diverted from calcite master branch. And to add some specific features they needed at a time. And now like calcite already has those features they once wanted. And so it's kind of like they need to like merge back to the calcite master branch so that we can start work from there. Yeah, that's it.
I think she's the best person to ask that question, by the way.
The transaction?
The real one.
Yes.
Transaction, you want to answer that as well? Or so for transaction, when Phoenix wanted to do that initially, the plan was to see whether like Tephra made sense, Omid made sense, or there's another engine for implementing the percolator paper from I think Xiaomi. Anyway, so we went with Tephra because Omid was not available. Omid is now kind of available in the Apache sense. There's no like effort going on, as far as I know, to re-implement the stuff on top of Omid. But that's again like there's still an open question of like whether we should do it the Omid way, the Tephra way, or again like keep both transactional and non-transactional differently for the time being, kind of thing.
Cool. Thank you.
Okay.
Can you go back to that materialized view slide? So I just wondering, you know, why? Let's say if we create this materials view ordered by MID, so for some queries, I think probably it would be better, right? I mean, what's the decision that it ordered by name instead of ordered by MID? This materials view.
I don't really understand your question. Is it about a query or?
No, I mean this in this example, right? It's ordered by name. So why not order by MID? I mean, of course, it depends on the specific queries, but there's a case where order by MID would perform better when the query has this MID greater than 100.
You're saying about this materialized view, right?
Yes, yes.
Yeah, sorry, I didn't have time to explain this slide really in detail.
Okay.
But this is like if you look at this the materialized view definition, it's kind of the definition query.
Okay.
So it's actually explaining the SQL representation of a Phoenix secondary index. So Phoenix secondary index is actually a different projection of the original data table and ordered on a different dimension.
Okay, okay.
Yeah. So actually, this is the representation, the SQL representation
I see.
of the
So then in some case, then it will use the actual table instead of through this materials view, right? If it's ordered by MID greater than 100, probably it's better just get it from the the actual table that where the primary key is MID, I believe, right?
Again,
Sorry. So in query, like where there's a select something where employee ID greater than 100,
yeah.
if it look from this matrix view, I don't think that is optimal, right? Because this is ordered by name, right?
Yeah, but no. Actually, let's go back to the very first page of this example. I
Okay.
should have just, like, here, this is
Yeah.
about, I mean, the two diagrams is about how we do this third query here. I select from employee
Yes,
ID
yes,
where,
yes.
yeah, from employee table where employee ID is greater
than
than 100 and ordered by
by
name.
name.
This is the original query. So we actually have two potential approaches here. One is we use the original employee table and do a filter on top of the table and then do a order by, right?
Yes.
And that way we can do a range scan on top of the whatever employee table because the employee ID is the primary key. But
Yes.
the cost, the extra cost is we have to do an order by, right?
Yeah.
Yeah, that's the.
Oh, that's why. That's the matrix view.
Yeah,
we
that's
have.
the left diagram is what the left diagram is about. So this is
okay.
the
I
first
see.
choice that you can use the original employee table, so that you can turn it into a range scan. But the cost is, the overhead is you have to do a sort, and then the other approach is kind of you can use the index table, and the extra cost is you have to do a filter instead of a range scan, right? You have to do a full scan on the index table and then apply a filter,
Yep.
and then do an extra project.
Yep.
Although in real life, costing, the project is going to be ignored anyway, but it's just an illustration of like how you compare the two approaches by
I see.
cost. Yeah.
Okay. Second question. Where do we store the? I mean, do you guys store the either CalSite or Phoenix store the cost? Like how many rows of this table? Does it store it somewhere or not?
It does. It does cache some of the costs, like on those nodes, like during runtime, like during planning. It does cache some cost.
Oh, during
Yeah.
planning, not during the ingestion or when the data being inserted into the table.
I mean, this is actually
In our guide posts.
yeah. This is actually two different ideas. One is one is the cost, and the other is how, like, based on what you get a cost. It's based on the statistics you get a cost, right?
Okay.
I mean, for example, like the simplest way could be like how you cost the table scan. Probably you are just going to like say we're going to cost the table scan as the number of bytes from that table.
Okay.
So, and the number of bytes is actually the statistics you store in Phoenix, statistic table, right?
I see. I'm thinking
And
about
then
the number of the rows, like the number of the rows.
The
right?
number of rows is also part of the statistics, but the way you cost a node, like runtime at planning time, you cost a node. For example, like for a sort node, it's if you decided to cost it like log n, it's going to be like number of rows, like multiplied by log of the number of rows. So the number of rows is the information you get from the statistic table, while the algorithm you use to cost that node is up to the user definition. And you use that input. It's like a function, whatever. So you use that statistic input, and then you apply, the cost algorithm, and then you get the exact cost for that specific node.
So that statistic table, when is being created?
Statistic table is part of the Phoenix features we just talked about.
Okay.
So it's independent of this outside thing.
I
Because we
see,
are
I
already
see.
using the statistics for.
I see. So the statistics
Yeah.
already there. It's just CalSite
Yeah,
using
exactly.
that statistic.
Yeah, exactly. Yeah, so actually, like during H-based compaction, like
Oh,
yeah, when we're going through all the like the cells of the table, it's doing kind of like collecting the byte number, the row count, yeah.
So
And
does
then
it mean that when the ingestion happen, it does not have the statistic yet, right? Before the compaction running.
could
It does not have? Okay, so then someone needs to create.
If you have the edge-based table, you have a count coming and you need to count your rows. I mean, it does not keep anywhere.
But it has to store this statistic, right, somewhere.
yeah, there are two ways actually of kickstart this statistic collecting.
Okay.
One is like it's just in the background. If you do a whatever, if in the background HBase is doing a compaction, it just gets automatically collected and stored in the statistic table. And the other way is you can just type a command there, like
Oh, create the statistic or something.
Update stats.
update stats.
Oh, update
yeah.
stats. Okay, so
yeah.
that will take some time to update the stats.
Yeah.
I see. So the first query that before the statistic being created.
Actually, the short answer is there's no point of talking about cost-based optimization without statistics at all, right?
So then it would be slow, right? That's my.
I mean, probably. I mean, most of the queries you don't have much choice other than scan the table, right?
That's
But
true.
sometimes you do have a dilemma, and that's when you need a cost-based optimization.
I see.
Yeah, but if you realize that your use case is going to need that cost-based optimization, you have to run that update stats or whatever. You have to update your stats anyway.
So yeah, I was not about to,
Yeah.
I was just curious at the beginning, like when this statistic being created. That's the only my question.
Anyway.
So yeah. All right. Thank you.